The enantioselective oxidative Hack reaction overcomes several limitations of the traditional palladium-0 catalyzed Hack coupling and has subsequently allowed for intermolecular couplings of challenging systems such as cyclic enones, acyclic alkenes, and even site selectivity on remote alkenes. CH activation decreases step count and hence mass intensity of chemical processes. That said, the selective cleavage of unactivated CH bonds remains an active and comparatively difficult area of academic research. Consequently, the use of precious metal catalysis in high loadings, stoichiometric metal-based oxidants, high temperatures, and directing group manipulations are often required. Until now, practical and economic considerations have presented the major barriers to industrial application. In order to form this substituted alkene using CH activation, we need an electron donating group on this benzene ring. Add that with an alkene in the presence of palladium-2 and benzoquinone. Because of palladium-2 catalyst, this is now referred to as oxidative Hack. Here are some examples of electron donating group. Anything that can donate electrons, your amide ester, hydroxyl, your methyl, halogens, you get the point. Now let's understand the mechanism. We start with palladium acetate. The oxidation state is 2. So first thing is going to happen is CH activation. Your H and C are going to break. So your carbon hydrogen bond is going to break. And this H is now going to grab that acetate from this palladium, forming this acetic acid. After that, your aryl is free to coordinate with palladium. So this is how it's going to coordinate in this manner. You're going to draw this carbonyl pointing towards palladium because there is some attraction, but it's not a bond. Step 2 is going to be complexation to palladium. So your alkene is going to come and it's going to behave as a neutral ligand. So the oxidation state still remains 2. Step 3 is going to be carbopalladation. So here your double bond is going to grab that aryl group. This coordination with palladium is going to break. And now palladium's coordination with that double bond is also going to break and it's going to attach to this carbon. As you can see here, this is the complex which is going to be formed now. Your R group is going into the page and your aryl is still into the plane, right? So the rotation must happen. Your aryl group has to come outside in order for beta hydride elimination to take place. So now you see your aryl is now pointing outside, right? It's coming out of the page. So now this palladium is going to grab that hydrogen. You're going to have that beta hydride elimination to form this substituted alkene. At the same time, you have an acetyl group and H on that palladium. That's also going to come off, forming this acetic acid. Now you're left with palladium-0. In order for this cycle to continue, the palladium-0 has to undergo oxidation to form palladium-2. And that's where benzoquinone comes in. So here's the chemical structure for this. Now we generated 2 acetic acid. So your acetic acid are going to be deprotonated, forming this acetate, which are going to now coordinate with palladium, which will make this cycle continue.